Now we're entering into part 2, which was our segment on electronics for radiation detection. And these are the two key concepts for chapter 16. The first one, though, you'll note is kind of applicable to the entire second part of the course. So we have the goal of a pulse processing system is to take a burst of charge as created through energy deposition from incident radiation and shape it into pulses whose number and/or amplitude can be counted at the end. Number 2, the first stage of pulse processing is preamplification, which takes the burst of charge, amplifies it, and then returns to a baseline value through some RC time constant. So you'll recall we had this figure from chapter 16 where we started with some sort of incident radiation coming through my detector, and it deposits energy in my detector material. And like we had in key concept number 1, this is a blip of charge or a blip of current. And I have my current pulse right here. Now that current pulse goes into my preamplifier, and the job of the preamplifier is to take this blip and turn it into a tail pulse. So we know that the output of the preamplifier is a tail pulse, and the thing that we care about is the amplitude of this step here, this delta V step. That delta V step is going to get passed on to my shaping amplifier, and that usually has two parts, the CR and the RC circuit. We'll talk about those more in the next section here. But then the shaping amplifier takes that and converts it. It takes this delta V and converts it into some sort of Gaussian, the Gaussian amplitude here is V sub peak, and V sub peak is somehow proportional to delta V. And then these Gaussian shaped things get passed on to our later circuitry, such as an MCA or a counter, or TSCA, that kind of thing. So let's talk about one thing that we really could describe here mathematically with the preamplifier, which is the subject of chapter 16. So if I were to make a plot where I have time and I've got voltage, I know that the output of my preamplifier is going to be some sort of step function, and that step function, as we know, has an amplitude of delta V. And the question is, how big is that delta V? Well, I know that it's going to be equal to the charge that is created in my detector, ideally proportional to the energy deposited, divided by the capacitance. Now this is the capacitance of the detector, but I also have my preamplifier, and you recall the preamplifier is going to look something like this, where I will have a resistor and a capacitor in parallel with each other, and I have tau, the shaping time of my step function here. So what is the decay time here is related to the RC time constant here. So here's my RC time constant associated with this preamplifier. Moving on to chapter 17, we talk about shaping, pulse shaping, counting, and timing. So the first key concept, the shaping amplifier takes the fast rise output of the preamplifier and converts it to a Gaussian-like pulse whose amplitude is proportional to the amplitude of the preamplifier step function. Number 2, analog pulse shaping usually happens with a CR-RC network. The CR differentiator, also known as a high-pass filter, takes a step function and returns a tail pulse. The RC integrator, also known as a low-pass filter, takes a step function and returns a slowly increasing function. The combination of the two can resemble a Gaussian. So here I just briefly remind you what this circuit is going to look at. First, we're going to have, some sort of input here, and I'm going to have a capacitor to an amplifier, and I'm going to have a resistor down to this bar down here, which is frequently ground, and then I'm going to have a resistor here like so with a capacitor. Okay, so this is my circuit here. I have C, R, and then I have RC. So that's my CR-RC circuit. Okay, so now let's talk about what the outputs are of each of these things. You remember that what's coming in is a tail pulse, and the length of this tail pulse is long, so it's just going to look like a step function here, and the amplitude is delta V, and that's what we've learned about in chapter 16. So what the CR circuit is going to have for its output is a tail pulse also, okay, and I'm going to call this C1, R1, and this is going to be R2 and C2 here. So I have tau for this function is equal to R1, C1. In the nomenclature that's used in the book, which is what I'm going to stick with, this is called E out. Okay, E out is a function of time. Now, for my my RC integrator, which is my low-pass filter, my E out as a function of time is going to look something like this. It's going to build slowly, low pass. And again, we have the RC time constant here is R2, C2. So we've got two different time constants here. They could be the same, but just so you know. Now, you remember that we solve differential equations based on these two different shapes. And what I get for the high-pass filter, my differential equation is E out plus tau E out dot equals tau E in dot. And for the low-pass filter, what I get is E out dot plus 1 over tau E out equals 1 over tau E in. Okay, and be sure that you're using the correct taus here. So in class, we went over many different explanations and examples of how to solve those first-order linear differential equations. Last thing I want to get to is what the overall output looks like, which is that E out, and this, by the way, is going to assume that tau 1 is equal to tau 2, or RC1 is equal to RC2. So E out is going to equal E over something called n factorial, t over tau times n, or to the n, and then e to the minus t over tau. N here is the number of RC stages. Usually we see CR, RC to the n. Now what I drew on the previous slide, n equals 1. But if we have multiple RC stages, then n equals the number of RC stages, and this is what the output looks like, assuming an equal time constant. Now we're on to Chapter 18. Chapter 18 was the multi-channel pulse analysis chapter, and this kind of wraps up everything on the electronic side. Here's where we actually start trying to quantify what's coming out of our electronics with the MCA. So we say that multi-channel analyzer takes a Gaussian input pulse and records its amplitude in a channel bin, which is how spectra are recorded. Now you'll note I have the word channel underlined here. In your notes, it very well may say records its amplitude in an energy bin. That's a change that I want to make here. Channel bin, a channel is just a number. Energy implies that we have done a calibration already. So when the MCA records something, it doesn't know anything about what its energy is. It just puts it into a channel. So that's why I've made that change. Number 2, MCAs can use several techniques to do this, but the goal is to have as linear, both integral and differential, a response as possible for all pulse heights and count rates. This chapter really is pretty straightforward, so I'm going to give you one equation and a couple plots. First, we have something called resolution. The resolution of our spectrum is the full width at half maximum of a peak divided by the centroid of that same peak. Now, the full width at half maximum is something that we know is represented by a Gaussian, but the mathematics of a Gaussian do not talk about full width at half max, they talk about standard deviations. So if I wanted to write this in terms of standard deviation, this is equal to 2.35 times the standard deviation divided by the centroid channel. Now we talked also about integral linearity and differential linearity. So if I were to plot, this here is going to be the integral linearity, and this is saying that across all channel numbers, my pulse height is going to increase linearly. Okay, so that means if I double my pulse height, I double which channel number I wind up in. Differential linearity, on the other hand, says that all channels are given the same weight. So if I look across all channel numbers and I give 1,000 counts in every channel, I look at my counts per channel, and this should be flat. Okay, and what that means is that each channel is the same width, essentially. So I don't have one channel that gets more counts in it than another. And that's all of Chapter 18, and that's all of Part 2.